Hello, everyone. Welcome to Fundamental of Computing. My name is Paulo Santos. I'll be your lecturer this semester. First and foremost, uh, this is the book cover, and it's an excellent book, and you're definitely going to need it to follow the course and to do the assignments and the modules. Um, You don't need to have the 8th edition, although it's advisable. But there are many other previous editions on the library that are also very good, and there is an online version as well that you can buy at a discount price, I believe. So we're basically going to read almost all of this book, and all of the exercises are based on this textbook. So yeah, I can't stress more the importance of this book. So we're going to start on chapter 1 today, an introduction to computer science. And please read the book. So don't rely only on the lectures. Ideally, you'd read the chapter before the lecture so that it doesn't become that boring thing of a lecturer telling you everything that you should learn. But actually, it could be a kind of discussion. So you could ask questions about topics that you didn't understand from the chapter. And obviously, we don't learn in one go. We are not in the matrix. In the matrix, that it's like some sort of connectors on the back of your head to upload information. So we learn by seeing the same thing over and over again. So I highly recommend you to read the chapter of the book beforehand. The book and the course is organized into these modules. So the first module, let me get a pointer here. Okay, 10. So the first module will be, we're starting with chapter 1 today, and next week we're going to see chapter 2, and the other week on chapter 3. This will complete the first module, which is called the algorithmic foundations of computer science. And that's the first assignment that you're going to have to deliver on week 3. And then we're going to go through chapters 4 and 5, which is hardware world. We're going to see a little bit of computer organization. Then we're going to go through virtual machine and operating systems. We're going to get a piece of this a software world input here, where we're going to learn Python. And then we're going to see a number of applications such as cybersecurity, computer vision, robotics, artificial intelligence, and at the very top, social issues of computing, and mainly ethics in computing. So the learning objectives of this first lecture is to understand the definition of the term algorithm, which is the main topic of the entire course. If there is one thing that you should learn from this topic, is what an algorithm is, how to write down an algorithm, and what is algorithmic problem solving. This is the bulk, the core concept that we want you to learn in this topic. So first, learning objectives, not only for this lecture, but for the entire course, is understanding the definition of the term algorithm, understand the formal definition of computer science, write down some very simple everyday algorithms, determine if an algorithm is ambiguous or not effectively computable, understand the roots of modern computer science in mathematics and mechanical machines, and summarize the key points in the historical development of modern electronic computers. Introduction. So what is computer science? Well, if we were face to face, I would ask you to do this word count, but as we are not face to face, and this is a recorded lecture, I'll just point to a few misconceptions of what computer science, what people think computer science is. So they think that computer science is the study of computer. This is as true as defining astronomy as the study of telescopes. That was a famous quote from a great computer scientist, Dijkstra. We're going to learn Dijkstra shortest path algorithm, I think on the lecture about AI. and certainly on computer networks. Computer science is the study of how to write computer programs. That's almost right, but not quite. It's almost as true as defining astronomy as the study of how to build telescope lenses. This is what this quote is by me, right? Computer science is the study of the uses and applications of computers and softwares. It's almost the same as saying defining astronomy as the study of the uses and applications of telescopes. No, these are all misconceptions. They're all wrong. So computer science is essentially the study of algorithms, including the formal and mathematical properties, which we're going to see in the next lecture, their harder realizations, which we're going to see in the second module, their linguistic realizations that we're going to see in the third module, and their applications, which we're going to see in the fourth module. So this definition of computer science as the formal mathematical properties of algorithms, the harder realizations, linguistic realization applications, is reflects of the structure of the book and the structure of this topic. Right, so we all know what computer science is. The study of algorithms. Right, so what is an algorithm? A basic, everyday definition of algorithm is a recipe. A cake recipe, for instance. An algorithm is just, in a very general sense, an algorithm is just an ordered sequence of instructions that is guaranteed to solve a specific problem. So, for instance, you have a sequence of steps. In each step, you have an action. So, in step 1, you do something. Step 2, you do something. And then, once you're finished, you stop the algorithm and finish your task. I assume that the algorithm solved a particular task. There are a few operations that are used to compute to write most algorithms. Well, the algorithms that we're interested in, at least in this topic and in computer science in general, there is what's called sequential operations. These are operations that carry out a single well-defined task. Or conditional operations that ask a question and then the next operation is then selected. So, for instance, if the water is boiling, put in the in the recipe that you're doing, right? A sequential operation in this case that put the water to boil. Conditional operations: if the water is boiling, do something with this. And obviously, iterative operations, there is what we call loops. So we say, while you are pouring the boiling water, you stir the dough, right? You stir the dough to make a cake. So these are loop instructions to tell not to go on, but to go back and repeat the execution of a previous block of instructions. In this case, is while you are pouring the water, keep on moving, keep on stirring the dough. Once if you're not pouring the water anymore, then you can stop stirring your cake recipe and do something else. I don't know. Put it in the oven. I never baked a cake in my life, so it was a terrible example to start with. A better example, extracted from the book. So please, again, I'm not sure if I told you, read the book. Is programming your DVR or programming your I don't know, your alarm clock or something, or any programmable tools that I'm sure that you've had to do these sequences at least once in your life. Step 1, if the clock and calendars are not correctly set, then go to page 9 of the instruction manual and follow the instructions there before proceeding to step 2. So you need to first set the clock and the calendar. This is our first instruction. Now this is an iterative instruction, what we called here, what we'll define here, these looping instructions, which is repeat steps 3 to 6, step 3 through 6, for each program that you want to record. enter the channel number that you want to record and press the button labeled channel. Step 4, enter the time that you want to record to start and press the button labeled time start. Step 5, enter the time that you want recording to stop and press the button labeled time finish. This completes the programming of one show. So let's say you want to record another show. If you do not want to record anything else, press button labeled end program, and then you go to step 7 and turn off your DVR, and now the DVR is on timer mode, ready to record. Now, if you do not want to record anything else, what if you do want to record something else? Then what it's doing here is that repeat steps 3 to 6 for each program that you want to record. So if this is false, meaning that if you want to record something else, you come back here and repeat the sequence of instructions again until you ask again, do I have another program that I want to record? Yes, then I come back here and repeat this over and over again. All right, another algorithm that we know, since we were all, I don't know, year 3 or year 4, is a simple addition, right? So you're adding two digit numbers. Let's pick up to a 2-digit number. So 47 plus 25, right? So you do this, you do 47 plus 25. So what you do here? You add first these 2 digits, 7 and 5, which is what? 7 and 5 will give you 12, right? 12 here. This one goes up, and then 4 plus 2 plus 1 is 7. Oops, sorry about it. It's 72. This mouse is a bit funny sometimes. Right? So this is exactly what I did here is exactly what this algorithm does. But here I'm writing in I'm using algorithmic representation. Right? So I want to add 2 digits. So you know there was a carry digit. What is a carry digit when I had 47? Sorry about it. Let's see if I can write this properly. 47 plus 25. 7 plus 5 is 12. The 1 goes up. This is the carry digit. Then I need a variable here that is carry. This is equal to 0 initially, so I have to initialize the variables. This is a counter. You can also initialize to 0. And I'll also initialize the digits. So this is the first digit of the number. The first digit is 4, which this 4. The second digit is 7, which is 7. And the same for the other 2-digit number, 25, where you have 2 and 5. 2 is stored in the variable b1, 5 is stored in the variable b0. Then is the iteration. We now repeat steps 4 through 6, while I is less than or equal to 1. First repetition of the loop, I has the value 0, so you add a0 plus b0 plus carry, which is what? 7 plus 5. Exactly what we did here in this, it's exactly what we do every day when we are summing any types of number. So a0 plus b0 plus the carry digit is 7 plus 5 plus 0. So the result I'll put in this variable c0, which is 12. Remember that I put 12. Now, because c0 is greater than 10, this is step 5, we reset c0 to 2. This is c0 now. And carry digit is 1. carry digit was put here, right? Repeat I to 0 plus, reset I to 0 plus 1. I is the step. Because I is less than or equal to 1, go back to step 4. Why does it need to be less than or equal to 1? Because I'm counting 0 and 1. I'm summing two digits. So I'm counting 0 is the first digit and 1 second digit. If it's greater, I don't need to do the sum anymore, right? So go to step 4. And what is the procedure here now? The procedure now, instead of A0 and B0, the sum will be what? A1 plus B1 plus the carry digit that is 1, which will be, that is the second repetition. It's written exactly here, right? Let me clean this slide. It's written exactly here. So add A1 plus B1 plus carry. It's exactly the same line here, which is 4 plus 2 plus 1. So C1 is 7. Because C1 is less than 10, we reset carry to 0. And we reset I to 1 plus 1, I to the previous value that it had, plus 1. This is equal to 2. Because I is greater than 1, we do not repeat the loop, but instead go to step 7. Set C2 equal to 0. And we print out the answer, which is these three digits here that were calculated. C1 was calculated in this first loop, which is exactly 7. C0 was calculated in the second loop, which was 2. And C2 is the remainder of the carry digit, which is 0. So exactly the result of the sum. Now, then you may ask, well, there's a lot of work to do. Just to do what? What I did is 47 plus 25, the stuff that we do every day. Yes, it is a lot of work. Machines are stupid. Computers are stupid. You have to tell the computer everything that it needs to do. It doesn't do it by itself. The stuff that we do, from talking over Zoom and play video games, somebody had to implement it. Somebody had to implement it. I know that if that's the first time that you see this kind of algorithmic way of solving problems, it may be a bit difficult for you. So I recommend you to read this part of the book, but we're going to start from next week. We're going to go slower and we're going to have some practice about writing algorithms. So this is just an introduction so that you know what this is the goal. I want to, in the next two weeks, you're going to be understanding this algorithm. You're going to be able to write similar algorithms. So I don't expect you to do it now, but I expect you to have at least an idea about what was done here. So this is an algorithm. It's just a very organized way of solving a problem so that a computer can solve the problem automatically. Automatically means somebody programmed the computer to do the job. All right. So this is the algorithm, the same algorithm that we did, written in a cleaner way. But now, instead of adding just 2-digit numbers, it's adding m-digit numbers, and then the number will be, each digit will be stored in one variable, and you can read it later. I won't get into details about this algorithm. Okay, so definition of computer science. Why are formal algorithms so important in computer science? Well, as I said, if we can specify an algorithm to solve a problem, then we can automate its solution. So there is this idea of a computing agent, a machine, a robot, a person, or a thing carrying out the steps of the algorithms, right? So if I have the algorithm written, if the algorithm is correct, then I can use a machine to solve the same problem or any types of machine, a robot or another person. So for instance, if I've never baked a cake, but I'm sure that if you give me a good recipe, I'll be able to bake it up to perfection probably. So it's just an organized way of representing a solution to a problem so that anything that carries the steps of the algorithm are able to solve the problems. Right, so there are obviously some problems are, they have algorithmic solutions. Some other problems are unsolvable, which we are going to also see towards the end of this topic. And some solutions are just too slow. And obviously, we don't have all the solutions of the world. Some solutions are not yet known. Maybe you can find solutions to these unknown problems, to the problems with not known solution in your PhD, right? It's one of the reasons for doing a PhD, trying to find solutions to open problems. Now we can propose a formal definition of an algorithm. It is a well-ordered collection of unambiguous and effectively computable operations that, when executed by a thing, by an agent, any agent, a machine, a robot, a human, a bird, produces a result in halts in a finite amount of time. Right? It doesn't work to have a solution that takes the age of the universe to finish. Right? We're never gonna get this information. Right? We're never gonna get the answer. We're not patient enough to wait to the end of the universe to get a solution. All right. So okay, formal definition of algorithm. It's a well-ordered collection. So upon the collection of operations, upon the completion of operations, we always know which operation to do next. It should be unambiguous and effectively computable operations. It's not enough for an operation to be understandable. It must also be executable, right? Or doable, effectively computable. If you have ambiguous statements in your algorithm, you have to go back and do it again, right? So these are actually examples of, sorry, got a little bit confused here. These are examples of ambiguous statements. So if in your loop, you should say exactly at which point you should go back. So repeat, now let's get our algorithm again. Here, repeat steps 4 through 6. It doesn't it doesn't work if you just say, oh, repeat until you get the results. No, repeat what? You should be specific. Repeat what for how long. So you should be as specific as problem, as specific as possible with your statements, right? So where you start, and from where what you repeat, and for how long, how many steps you have to repeat. And it's also produce a result in halts in a finite amount of time. Right, so we want a solution to a particular problem. So we want the result, some sort of result that is observable to a particular user. So it may be the answer of the algorithm, maybe a numerical answer, or maybe a new object, or maybe a change in the state of affairs of something, in state of the environment, or of the robot, or of the tabletop, or where the robot is playing with bricks. And whatever. So there should be an answer. If there is no answer, you can't say that your algorithm is working, right? It's useless. Right. What do I mean by unambiguous operation or primitive? It means that it's an operation that can be understood by a computing agent without having to be further defined. It's not enough an operation to be understandable. It must also be effectively computable by the computing agents. And we should also avoid infinite loops, which are repetitions that run forever. They are usually mistakes. So this is an example of an ambiguous algorithm. So you can get that's algorithm with the double quotes. So you can read this at the back of a shampoo bottle. I don't know why shampoo bottles have instructions to use instructions, but they do. Let's see. You can have a look at your shampoo bottle at home and see if it has instructions. So in this case here, given in this example given by the books, that the algorithm for washing one's hair is: first step, wet hair; second step, lather; third step, rinse; fourth step, repeat. So why this is not an algorithm? An algorithm in the formal sense that we say. We now have a formal definition of an algorithm. There should be a well-ordered collection of unambiguous, effectively computable operations that halts in a finite amount of time. Now, why this is not an algorithm? First of all, lather, rinse what? My dog or my chair? It's not specific. It's too vague. It's too vague. So lather what? Repeat which part? Repeat what? Rinse. So I just keep repeating rinse, or I repeat wet hair. Only wet hair. So I just need to keep repeat how many times? Forever? Will I be forever washing my hair? I wish. If I had hair, I could obviously. Though in my case, not even that is correct. And when should this stop? Should this process stop? So this is not. Although this may be understood as a kind of everyday algorithm, it's not a formal definition of algorithm. It's not computable. It's not. It doesn't have any of the characteristics of a formal definition of algorithm. It's a well-ordered collection of operations, but it's not ambiguous. It's not unambiguous. It's not effectively computable and doesn't stop in an amount of time. So that algorithm for washing hair is not an algorithm. It's just a sequence of steps. Now, this is a better algorithm for washing one's hair. First step, wet your hair. Second step, set the value of wash count to 0. This is the initialization of a variable, a counter, which is wash count. Repeat steps 4 through 6, so I know exactly which steps should be repeated, until the value of wash count equals to 2. So I'm going to do lather your hair, rinse your hair, add 1 to the value wash count. So wash count was 0. I'm going to execute this once, and then wash count will be 1. Let me clean this slide. So wash count now will be 1. It's still not 2, so I'm going to repeat lather hair, rinse hair, add 2 to the wash count. We'll add 1 to the wash count, it will become 2. And then wash count equals to 2. So this condition is not true anymore. So when it's not true, I don't repeat while until the value is 2. Now it's 2, so I don't need to repeat. And go to the next operation with stop. You have finished shampooing your hair. The end. Right? Is that understood? So another correct solution to the shampooing problem is doesn't have a loop here, right? So you see there's no repeat or anything. This is a more direct, only using single operations. Wet your hair, lather your hair, rinse your hair, lather your hair, rinse your hair, stop. Which one is best? We're gonna see which one is best next week. But obviously the answer to what is best depends on your application, depends on your interest. So if your application is very simple, like has only a few steps, this one is enough, right? So this one is enough. Solves the problem. It's correct. Has all of the characteristics of an algorithm. But if you want a more general solution that would work for any type of hair, long, short, and for many distinct kinds of person, to a model, a supermodel, or to someone like me, and that doesn't need to wash the hair because I don't have them. Now, if you want a more general solution, you should write algorithms more general. So this one only works for 2. This one is easily applicable to other people or to other types of hair wash. If you want just once, you just change this counter or this loop to stop when it's 1. If you want to wash your hair 100 times, you just change one number to 100 times. In this case here, if you want to wash your hair 100 times, wash, lather, rinse, you're going to have to write 200 lines. You're going to have to repeat these 2 lines. My mouth is terrible today. You need to repeat these 2 lines 100 times. So you're going to spend a lot of time typing, but the solution will be the same. So which one is best? In this case, obviously, this solution is best. It's better. All right. Okay. Obviously, there is we have to talk about the importance of algorithm problem solving, right? The development of algorithm, as we're going to see in a few minutes, we're going to talk a little bit about the history of computing. Obviously, the history of algorithms dates back from much further down the line, right? The proper word algorithm is from the Middle Ages. From the first people that tried to solve an algebraic problem in a kind of organized way, these were already understood as algorithmic problem solving. But once we go to computer science, well, we don't write computer programs without a computer agent, right? So when we talk about algorithms today, we're mainly thinking, well, in general, we're thinking about algorithms for computers. And these were largely used since the Industrial Revolution in a more restricted way. This was during the Industrial Revolution. There was mechanized and automated repetitive physical tasks. So there was already the idea of algorithm problem solving. But certainly, the idea of algorithm was essential for the computer revolution in the 20th and 21st centuries, which mechanized and automated repetitive mental tasks rather than physical tasks in the Industrial Revolution, with the creation of personal computers in particular. There was this need or this facility to automate repetitive mental tasks. And well, let's see a little bit about how this whole idea of algorithm plays throughout the history of computing. So the book cites as the early period of computing from the past up to 1940. In the 17th century, there was the automation and simplification of arithmetic methods for scientific research. So it was John Napier invented logarithms as a way to simplify difficult mathematical computations in 1614. The first slide rule appeared around 1622. Blaise Pascal designed and built a mechanical calculation named Pascaline in 1642. And Leibniz constructed a mechanical calculator called Leibniz wheel in 1643. So these are all pretty brittle machines. They were not computable, but they certainly, in their design, had the idea of algorithm and had the idea, mainly had the idea of computing. You are producing computations. You are solving difficult problems in an automated way. So this is the Pascaline, one of the earliest mechanical calculators. 17th century devices could represent numbers, could perform 17th century devices. I mean, all of these, the John Napier, the slide rule, or Pascaline, or Leibniz wheel. They could represent numbers. They could perform arithmetic operations on numbers, but they did not have a memory to store information. So they were not programmable. A user could not provide a sequence of actions or a sequence of operations to be executed by the device. They had to do step by step. So 19th century devices, I've read books that put the original computing in Joseph Jacquard was the inventor of the automated loom. They used punched cards and created patterns in 1801. So you know from your history books that the automated loom, which are things like this, automated looms are examples of the first programmable computers, and they were one of the main devices that were used in the Industrial Revolution in England. That modernized the whole, fermented the modernization of all of the other industries, starting from the textile industry, started from the automated, from the Jacquard loom. So you can see here, these are punched cards. These are actually codes. They're actually patterns. The machine would then read these patterns with these needles here. These needles here. The machine would read these patterns and then apply distinct patterns on the looming task here. So this is basically a computer, a mechanical computer, where a programmable computer. Because if you change the operations here, if you change the code, the machine is going to generate other patterns, right? So this is there's a link here that you could watch later. I'll upload these slides on Flow if they are not already there. Click on this and you're going to see the loom working. It's an example of the loom on YouTube. This is a YouTube site with a loom, with a working loom, automated loom from the 19th century. There were other 19th centuries computing devices, such as Hermann Hollerith. He was inspired by the Jacquard loom. They designed and built a programmable card processing machines to read, tally, and sort data on punched card for the U.S. Census Bureau. And he founded a very tiny and not important and very little, a company of little importance called IBM in 1924. It's the same IBM that we know today. It was founded by Hermann Hollerith, and it was basically founded to do the U.S. Census. U.S. Census were basically founded to do these programmable card processing machines for counting people, sorting data, and it was also answering questions. So this is a nice kind of example of the. This is an example of the Hollerith machine, a cartoon example of the Hollerith machine. This is a great book, kind of old, but very difficult to find a copy. This is from Bonnick's A Cartoon Guide to Computer Science. So as you know, census consists still today of asking a series of multiple questions, such as how many children do you have, and multiple choice questions. what's your religious preference, and so on and so forth. From this questionnaire, we want to know the total number of citizens, simple questions that at the same age, the number of citizens that had two children or a particular number of children, a specific number of children, how many were militants of a particular religion, as well as more complex questions such as how many fundamentalist vegetarians have more than 20 children in this example. So Hollerith proposed to put each person's responses on a single punched card of the size of a dollar bill. So basically in these punched cards you had each column was represented the question, and each column represented the question. Yeah, and each column represented a question, question 1, question 2, question 3, and each line represented the answer. So a punch on this location would say that question 1 had answer A, and question 2 had answer C. So this will be one card per person. And then these cards were read by a device consisting of a grid of little pins mounted on these springs and wired electrically. So as the cards pass through the machine, the pins where the holes were the pins that match the holes would make a connection with a circuit, with an electric circuit. So this one was an answer. There was an answer here because there was a hole here, right? There was a hole here. And each one of these circuits was connected to a kind of counter, and then you could run the totals of every possible response continuously as the cards were fed into. Right. So if you're going to talk about the Industrial Revolution, we have to talk also about the Luddite movement. So there are people originally opposed to the automation induced by it started with the Jacques loom, and they used to destroy the machinery as a form of protest. And you can still find this term used today to describe any group that is frightened or angered by the latest developments in any branch of science and technology, including computers. And this is obviously related to the conclusion of this cartoon is saying here, does it count the unemployed census workers? So this is a question for us to discuss throughout this topic, which is what are the social impacts of the science that we developed? What are the social impacts of the engineering solutions that we developed? And how can we mitigate the negative impacts? We should always think about it. All right. And also, in any introduction to computing, we have to talk about Charles Babbage. Charles Babbage designed what's called the difference engine, and he designed and built the difference engine in 1823. This engine could make addition, subtraction, multiplication, and division up to 6 significant digits. It was a terrific machine. It could solve polynomial equations and other complex mathematical problems. There is also a video of the Babbage machine that's currently a reconstruction of it is in the Science Museum in London, and you can see it running by clicking on this YouTube video. And okay, so we talked about a different machine, and this was a programmable machine, right? This was Charles Babbage designed a programmable machine. It was programmable to solve arithmetic problems, not only to do census and not only to create patterns in textile, but it was also to solve other arithmetic problems, such as polynomial equations and other complex mathematical problems. But you need to have a programmer. So, who was the first programmer in history? Do you know? Can you guess? It was the daughter of Lord Byron, the same one that was a poet, and I think he was a member of Parliament in Britain in the 19th century. This is Anna Byron, or the Countess Lovelace, or Lady Lovelace. She was the first programmer in history. So she was not hired. I think she was a part of the nobility in England. But she worked with Charles Babbage with the analytical engine, with the difference engine, and she was the programmer of Charles Babbage. And she developed a number of programming languages that were quite advanced for the time. Later, Charles Babbage designed an analytical engine which was very close to had a similar structure to a modern day computer. Unfortunately, no one wanted to sponsor him to build the machine. He designed the machine but never built it. In the machine, as we're going to see in our lecture on hardware, it had all of the parts of a modern day computer, such as an arithmetic and logic unit, a memory, a processor, an input and output. Right? There's here another YouTube video with this is actually a talk, a 1 hour talk about how difficult it is to construct the Charles Babbage analytical engine. You have to have in mind that this is 19th century. They didn't have microprocessors. So this was a mechanical computer. And this is a piece of Charles Babbage design. All of these items here, you can, if you don't know what I'm talking about, wait for the hardware lessons for 2 weeks time, or 2 or 3 weeks time. Each of these hardware elements were all mechanical. Right? Yeah. So parts of this machine, the analytical engine, was recently built. I think also in the British Museum, in the Science Museum in London. I'm not so sure about it. So there's a whole story of how this was built in this link. Right. So as I just said, in the 19th century, the computing devices were mechanical, not electrical. But they had many features of modern computers. They could represent numbers and other data. They had operations to manipulate data. They had memory to store values in a machine-readable form. This is important to notice. And they were, most importantly, they were programmable. You could input sequences of instructions to the machine, and then it would repeat automatically this sequence of instructions to do complex computations. Now we go full circle. What we are talking about here, these machines could understand algorithms. So you design a solution to a problem in an algorithmic way, as we saw in the first half of this lecture, and input in this machine, and the machine will just execute it. All right. So this is the early period of computing up to 1940. So what happened in 1940? So what was happening at that time in the 20th century? Second World War, right? Second World War. And there was a rush from both sides, from generating coded messages and from decoding the messages. And the first computer ever built was German. It was built during the Nazi Germany. It's called SUSY Z3 in 1941. It was the first fully operational digital computer in the world, with 2,600 relays, 800 for memory, 600 for computing, and 200 for tape reader. A small display keyboard unit for inputting programs, with a memory of only 64 characters. But this was enough to some historians say that this would be enough to extend the war for more decades. But luckily, Hitler didn't like the idea. It was too modern for his very tiny mind. Thanks heavens, right? So SUSY was never used in the war, although it was projected and constructed, whereas the British built the Colossus in 1943, which was a general purpose computer, was designed by Alan Turing. So I don't think Alan Turing built it, but he definitely designed it for the British Enigma project, and that was the computer that was used to break the German code and help the Allies to win the war. Later, in 1944, there was Mark I, which was an electromechanical computer used a mix of relays, magnets, and gears to process and store data. This is now in America. The Mark I is an American computer. And the ENIAC was the ENIAC for the electronic numerical integrator in calculators. Was created in appeared in 1946. Was the first publicly known fully electronic computer. All of these were kind of secretive projects. Also military Germans here, military British, military Americans, and this was the first kind of civilian, publicly known, fully electronic computer. And this is SUSY Z3. I've seen a copy of it in the Bremen Museum of Technology. This is Colossus. Colossus was destroyed after the war, and the project was dismantled and was kind of hidden because, these things are. So as it was a military project, it's all kind of everything classified, even today. But this was a surviving photograph of the Colossus machine. Mark I is this beauty here. I think you can see Mark I in Smithsonian Museum in Washington, D.C. And this is ENIAC. All right. So, the birth of computers. We are now in the next phase of computers, the birth of computers from 1940 to 1950. One of the key figures in this in the development of computing, and we are gonna spend 1 hour talking about his design, which is the von Neumann machine, is John von Neumann. John von Neumann proposed a radically different computer design based on a model called the stored program computer. It was a research group at the University of Pennsylvania built one of the first of such machines. It was called EDVAC in 1949. EDVAC 1 was the first commercially sold computer, and nearly all modern computers use the von Neumann architecture that we're gonna see during this topic. And this is von Neumann, and this is von Neumann next to I think this is ENIAC. I'm not sure if that's EDVAC. But von Neumann, please look into him. He was also part of the Manhattan Project. He knew a great deal of nuclear physics as well. He was a genius. One of the greatest minds in the 20th century. Right. So the modern era from 1950 to the present. So the first generation of computing devices, which were similar to the EDVAC, they were built with vacuum tubes for processing and storage. They were extremely large, expensive, and delicate. It required trained users in special environments to run. The second generation was from 57 to 65. They were computers based on transistors and magnetic cores instead of vacuum tubes. Don't worry if you don't know what a vacuum tube is and what it is for, or a transistor. We are going to see it in the hardware version. So basically, bear in mind what a computer. The only thing the computer does is to process zeros and ones. And what these things were doing were just a vacuum tube is like a light bulb. I have a picture of it later on, which is on when it's when the light's on, and it's off when the light's off. This is 1 or 0. 1 lights on, 0 lights off. And yeah, transistors are a lot more complex than this, but basically the function is the same, and we're gonna see in the hardware lecture. And this was the beginning of the first proper high-level programming languages such as Fortran and COBOL. This was a first generation of computing. The first generation was computers built with vacuum tubes. Second generation was computers built with transistors and had high-level programming languages. The third generation was the era of integrated circuits. In the birth of the first mini computer, they were the size of a desk, and not the size of rooms like the previous generations. And there was also this period from 60s to 70s, mid 60s to mid 70s. They also marked the birth of the software industry. And the fourth generation from 75 to 85 was the first microcomputer, which was a desktop machine. And personal computers, right? The personal computers started in this period. The development of widespread computer networks, the beginning of electronic emails. Finally, we have email. The development of graphical user interface. This more towards the end of the 80s, and embedded systems. This is the family of vacuum tubes. As I said, these are I'm kind of exaggerating, but they look like light bulbs, aren't they? Essentially, they are. Slightly more complex than light bulbs, yeah. So they could answer a question, a yes/no question. They could represent 0 and 1. Of course, if I have 2, I could represent more zeros and ones, as we're going to see, and we're going to calculate in the harder lessons. So this was the let's see, from this you have a kind of the whole history. In the 40s, you had vacuum tubes. This is a point contact transistor, a kind of a very early version of a transistor. This is a proper transistor of the kinds that we see today in discrete electronics. Very similar to this. And these are designs from the 50s. In the 60s, as we've seen in the previous slide, was the birth of microchips. So the first microchips contained 2 transistors. And more recently, obviously, in the 90s, we had a more modern microchip. They contain as many as 5 million transistors. That's why we can encode a lot of information. If one vacuum tube can say 0 and 1, what can we do with 5 million transistors? Most of the computations that we could do at the end of the 90s. Of course, today we have more powerful machines. My mobile phone has more processing power than this microchip. A lot more. And the 5th generation dates from 1980s, 85 till today. We've seen massively parallel processors capable of quadrillions, 10 to the power of 15 computations per second. Handheld digital devices, mobile phones. Finally, we can spend all of our time looking crap at the internet with a quadrillions of computations per second. Powerful multimedia user interfaces incorporating sound, voice recognition, video, TV, and YouTube. Finally, YouTube videos. We can spend all of our time watching silly YouTube videos. Wireless communications, mobile phones again. Massive cloud storage devices. Cloud storage, Dropbox. This is one of the most famous cloud storage device. Ubiquitous computing. What is this word means? Ubiquitous. You can find computing anywhere. Anywhere. Now, today you can buy with this Internet of Things thing, that we are going to discuss Internet of Things at the end of this course, but basically Internet of Things is that every single thing is a computer. It is connected to the Internet and is doing processing and is in sort of with some artificial intelligence, and they can talk to each other. And I sometimes receive email from my refrigerator. My refrigerator can send me emails. And I have a light bulb at home. It's connected to the internet that I can't access anymore because I lost the password. Yeah, I lost the password of my light bulb. That is Internet of Things. Right. So also ultra high resolution graphics and virtual reality computer games. Okay. Let's go back to the course now. We're not going to see. Okay, there's a whole bunch of stuff to see. We're going to be talking about a little bit about these things during this topic. But if you want to learn how to program games, you're going to have to do another topic. If you want to know more about cloud services and networks, you have to do another topic. You have to, if you want to know video processing, you have to do my computer vision topic later. And now, let's go back to the stuff that you have to learn in this course. Let's wrap up. Then, as we said, computer science is the study of algorithms, including their formal mathematical properties, their hardware realization, their linguistic realizations, and their applications. And we're going to see the formal and mathematical properties is the level 1. And this is all contained in the module 1 of that you have to do within 2 weeks. I think week 3 you have to do module 1, which is the algorithmic foundations of computer science. The module 2 is hardware realizations. These are all contained in the book in the hardware world and in the virtual machine. And we're going to see the linguistic realization, which is the software world, and then applications and social issues. This is all what makes the book, and this is all contained in this topic. And thank you for the audience. I hope to see you again on the online lecture. Again, please read for next week, read chapter 2. Now, if you have to do one thing in this topic, just one thing, read chapter 2 and understand it. Because that is the discussion of algorithms. And as I said, as the book says, computer science is the study of algorithm. If you don't know what an algorithm is, if you can't solve problems in an algorithmic way, you won't be able to understand the other stuff. Well, you will, but you won't actually be able to assimilate it in the way that we expect you to. So please read chapter 2 for the next lecture. Thank you.